just draw it, something like that. This is oversimplistic, but it gets the point across. And there's a region on the protein that allows it to bind to and recognize some other compound. I mean, if this is going to be an enzyme, it has to bind to reactants of a chemical reaction. If this is a signal molecule, it has to bind to a receptor. If this is a receptor, it has to bind to a signal. Right? So binding is a very important property. So there is always a region, right? And we often will call that region the active site, where a protein will bind to something. Now, the molecule, and this binding is usually not covalent, because if it was covalent, that's too strong of a bond. We've actually created a totally new molecule, right? I mean, we want the bonding to be such that it could release at some point as well, right? So it's often non-covalent. So usually it's the result of interactions of opposite charges. Remember, negatively charged things will bind to positively charged things. And one type of binding chemical bond that we use repeatedly that is singly weak but collectively strong are hydrogen bonds. So this area right here is going to have a particular charge that might recognize something else. Now you have to realize that there are a number of shapes of things or different kinds of things out here that, I'm just making all this stuff up here as we go along, right, that could potentially bind to that. But because of the chemistry, and by the chemistry I mean both the shape and the charge, okay, there are only certain compounds that this thing could potentially bind to. It can't bind to everything. If it bound to everything, it'd be worthless. Right? It's selective in what it binds to. So this active site will have a particular, what we call affinity. So first of all, there's specificity. What does that mean? It means it's specific for what it will bind to. So there's specificity. So I guess these are characteristics of this protein interaction here. There's specificity, and that's due to what we call affinity. Now, affinity is just a fancy word for attraction. Now, if we look at this molecule here, the protein, is going to be specific for only certain things out here, these compounds. The ones that it will bind to we'll call ligands. Sometimes it's just called substrates. Now, what are potential? These are all, I guess, potential ligands here, right? But there are two of them that look like, just from my little picture here, might be better or more likely to bind than others. Which, can we rule any out? Do you think this one is a potential ligand? Probably not, right? It doesn't look like it shares enough structure. What about this one? This one? Yeah? And what about this one? No. Okay. So we've already determined that there is specificity, right? It is not general to what it binds to. It is specific to only binding to some things. Now, affinity is the degree of attraction of a potential ligand to the protein. So if we say something has a low affinity, it's a weak attraction. If something has a high affinity, it's a strong attraction. And of all of the potential ligands out here, these two here, they will vary most likely in their degree of attraction to the active site. So we would say that while these are both ligands potentially, they probably have different affinities. Could you make a guess as to which one might have a higher affinity and a lower affinity? Square. Which one do you think is the high affinity? Square. Square, right? I think that has a higher affinity, and this probably then is lower affinity. Okay. So even though we say that these are specific, they may bind to a number of different compounds, right? But those compounds that they bind to may have different affinities. So this would be the preferred ligand, if you will, right? And what if these two were present at the same time in the same amounts? Is there one that this would bind to first, you think?